Video 6-6, hybridization theory. Okay. So, using VSEPR, we could predict shapes of molecules. Now, there's another theory that comes up, which is hybridization theory. Okay. This helps to explain how the orbitals can overlap to form covalent bonds. Okay. Now, why do we need it? Well, let's go back and have a quick review. Okay. Remember the shape of an s orbital. An s orbital is basically just a sphere. Okay. The p orbitals had lobes on them, kind of egg-shaped, and you had both of these made up one orbital, and we had three of them. They're oriented in three different directions. Okay. Now, the problem with VSEPR is that if we just say, well, the atoms bond because the orbitals overlap, the normal molecular orbitals don't overlap well. Okay. Example, an s orbital from one atom and a p orbital from another atom will actually, they could overlap, but they produce the wrong bond angles. They don't produce the correct shapes. Okay, an example, methane, CH4. Okay, Lewis structure for methane should simply be this. Carbon has 4 electrons, so it'll share 1, 2, 3, 4, and it'll bond with 1, 2, 3, 4 hydrogens. Okay. Now, the shape of that is not square planar, it's a tetrahedral shape. Okay. And every single one of these angles should be 109.5 degrees. Okay. Now, the problem with that, okay, we want a hydrogen. A hydrogen is just simply a 1s orbital. That's where its one electron is. It has to come in and bond with these atoms. So, you say, well, okay, here's the carbon atom, and here's the three p orbitals. So one hydrogen will bond here, another hydrogen will bond to this one, another hydrogen will bond to this one. Okay, now where's the fourth hydrogen bond? Well, don't forget the carbon also has an s orbital, which is in the middle. So maybe bonds someplace down here, or whatever. Okay, but the angle between this orbital and this orbital, these right here, is 90 degrees. It's not the angle that is observed, 109.5 degrees. Okay, so hybridization theory came along. Okay, how does it actually turn into a tetrahedral shape? Okay, well, what happens is two or more of the atomic orbitals of similar energies on the same atom, so the orbitals on the carbon, can mix and produce the same number of new orbitals of equal energies. Okay, so what basically happened was the 1s orbital and some of the, whoops, not the 1s on the carbon, the 2s and some of the 2p orbitals actually mixed. They're similar in energy because they're both 2, but they're not the same. They produced, if we take 1, 2, 3, 4, that means I have to produce 4 orbitals with the same energy. Okay, now, this is the important part you need to know. Okay, and it's a simple part. How do you figure out the hybridization of a specific atom? Okay, well, what are the types of hybridizations we can have? Okay, well, simple. Okay, all you do is count the number of single bonds that you have and the number of non-bonding pairs on an atom. Okay, now, if you have a double bond, you only count one of them. Okay, if you have a triple bond, one of these. The other two are not single bonds. Okay, they're multiple bonds. So, in either case, if you saw a double bond or triple bond, your count is 1. Then you count how many more other bonds are on that atom, plus the non-bonding pairs. Okay, and if the total is 4, the hybridization of the atom is sp3. Okay, if the total is 3, it's sp2. The total is 2, it's sp hybridization. Okay, and if you only have 1, it's basically just an s orbital. No hybridization took place. Okay, now, what do these things mean? Okay, whoops, well, sp3 means an s orbital hybridized with 3 p orbitals. Okay, and you produce 4 sp3 orbitals. Okay, If it's an sp2, that means the s orbital plus only 2 of the p orbitals hybridized. And as a result, I took 1 plus 2 more, so I end up with 3 orbitals. The number you start with is how many you have to end up with, and these are called sp2 orbitals. Okay? And an sp was just an s plus 1 of the p orbitals, hybridized and gave me 2 sp orbitals. Okay, so figure out the hybridization for each of these each atom in the molecule. There is no hybridization for a molecule. Every atom has a specific hybridization. Okay, so let's look at this one first, C2H6. Okay, the arrangement, 2 carbons. Carbons have to share 4, so it'll share 1, 2, 3, 4, 1, 2, 3, 4. And then the hydrogens share 1 each. Okay, so that has to share 2 pairs, so you get 2 bonds there. Okay, so for this one, count how many single bonds you have. 1, 2, 3. Double bond, you only count 1. So since that's 3 of them, this is sp2. Okay, this other carbon, same thing. 1, 2, and you count only 1 of them. So that's also an sp2 hybridization. Okay, and the hydrogen only has 1 bond. So this is basically just an s orbital. Okay. C2H4. Whoops, sorry. This is C2H4. Let's look at C2H6 up here. Okay. Your Lewis structure is going to look like this. H and H. Okay. So for this carbon right here, you count the number of single bonds. 1, 2, 3, 4. So total is 4, so that means it must be sp3. Okay. Same on that carbon there. 1, 2, 3, 4. So that's also sp3. Okay. Now, what about C2H2? The carbons can only bond to 1 more hydrogen here. 1 here, 1 here. That means it shares 1, shares 1. So it has to share 1, 2, 3 more with the other carbon. So you end up with 1, 2, 3 bonds there. Hydrogens share their 1. Okay. So for each one of these, well, the hydrogen is just going to be an S because there's only 1. The carbon, you count 1, and the triple bond, you only count 1. So it's a total of 2, so that's an sp. Okay. This carbon, same thing. You count 1 from the triple bond, 1 there. So that's also an sp, and that is going to be an S. Okay. H2O. We know the structure of water by now. Okay. The hydrogens are always going to be S's because there's only 1 of them there. 1 bond that they can make. So that's an S. That's an S hybridization. Okay, not really hybridization. Now, for the oxygen, 1, 2 bonds plus 3, 4. Each one of these is a pair. So you count the non-bonding pairs. They count as 1. So 1, 2, 3, 4. So that's 4. That means it's sp3. Okay. Now, CO3 2 minus. Oh, let's erase everything here. Okay. Polyatomic ion, carbonate. So 2 minus, carbon in the middle, oxygen, oxygen, oxygen. Carbon starts out with 4, then we're going to add 2 more, so that's 6. Okay, don't forget, add those to the middle ones before you start. So 6. Now to bond 6, you share 2 with 1. Okay. 2, 4, that's 2, 4, 5, 6, 7, 8 up there. Okay, 2, 4, 6, 8 for the oxygen. Now, how do we bond through the other ones? Remember, get rid of those. Make a coordinate covalent bond going that way. Get rid of those. Make a coordinate covalent bond going that way. Each oxygen, important that you put in the non-bonding pairs. Okay, so this oxygen right here, what's its hybridization? Well, you got 1, 2, you only count 1 of them. So that's 3. When the total's 3, it's sp2. The carbon, 1, 2, 3. It's also another 3, so it's an sp2. This oxygen right here, 1, 2, 3, 4, so that makes it an sp3 hybridization. This one here also. 1 bond, 2, 3, 4, sp3 hybridization. Okay. And CO2, what's that look like? Well, OCO, double bond, double bond. 1, 2, 3, 4. Okay. The carbon, double bond, you only count 1. This double bond, you count 1, so total's 2. That's sp. Okay. The oxygens, 1, 2, you count the bond. 3, so that makes it sp2. And same here. Count 1 bond, 2, 3 pairs. So that makes it sp2. Okay, don't forget. Orbitals, 1 plus 2 more orbitals gives you 3. So it has to be the same as the number of bonds plus the pairs. Okay, now, what happens during hybridization? Okay, atomic orbitals on one atom will combine. They will hybridize. Okay, now, how does the atom know which one's the mix before it actually bonds with another atom? Don't worry about it. It just does. Okay, so what's happening? Okay, I went over this a little bit earlier. In an sp3 hybridization, the s orbital and the 3 of the p orbitals from the same energy level will mix together and make 4 of these hybrid orbitals. And each one of these 4 ends up with the same energy. Okay. sp2, it's an s and 2 of the p's. sp, it's an s and just 1 of the p orbitals. Okay. What's an sp3 hybrid orbital actually look like? Well, you can only have sp3 starting with energy level 2 because energy level 2 is the only one that actually starts with p orbitals. Okay, you cannot have sp3s and energy level 1. Okay, and which orbitals will hybridize? These have to be in the valence energy level. Okay, so you only get hybridization with the valence orbitals. Okay, so one of these combines with all 3 of these, and you produce something like this. Each one of these, okay, remember, these 2 make up 1 orbital. These 2 make up 1 orbital. These 2 make up 1 orbital. This is a separate individual sp3 orbital. This is a separate. This is a separate one. This is a separate one. Okay, in theory, there's another little lobe in the back there, but we kind of basically, because it's so small, that means the probability of finding electrons there is really small. Okay, so what happens? We get 4 lobes, 4 orbitals in a tetrahedral shape. Okay, in sp2 hybridization, you take s and only 2 of the p's. So this one right here, the pz orbital, the one that's sticking up and down, nothing happens to it. Okay, and you produce, this one right here is basically the same as the pz. Nothing happened to it. Okay, so this one right here is unhybridized. Okay, so you get 1, 2, 3 hybrid orbitals because you started with 1, 2, 3 atomic orbitals. Okay, now these all go into a plane, bond angle 120 degrees. So basically this will give you the trigonal planar shape. Okay, in an sp hybridization, basically just the s and only 1 of the p's, the purple ones here, will hybridize. Okay, and they're going to produce, basically, this is one sp hybrid orbital, this is the other sp hybrid orbital. Okay, so you only get 2 of them. And their bond angle is going to be 180 degrees. Okay, so from there to there, it's 180 degrees. And basically it's a linear shape. Okay, now, types of bonds that you can have. It depends on what kind of overlapping we have. Okay, and I will show you guys a demo in class also. Hopefully make it a little clearer. Okay, sigma bonds. A sigma bond. This is a great Greek symbol for sigma. Okay, and that's actually lowercase sigma. The overlap is symmetrical around the bond axis. Okay, and in a pi bond, the overlap is above and below the bond axis. Okay, what does that mean? Okay, this is not an octopus. This is ammonia, NH3. Okay, the Lewis structure for ammonia, one pair of non-bonding, H, H, and H. Okay. Now, each one of these is an sp3 hybrid orbital, each one of the purple ones. Okay, how do you know it's sp3? Well, look at the Lewis structure. 1, 2, 3, plus the non-bonding pair of 4, so it must be sp3. Okay. This is a sigma bond right here. One of the hybrid orbitals basically overlaps end to end. Okay. So when you get an overlap that is going end to end, okay, then this is a sigma bond. Okay. Now a pi bond. A pi bond forms basically when p orbitals. This right here is not a pi bond. That is a sigma bond. Okay. It's overlapping end to end. Okay. Pi bonds, you have to have p orbitals. Okay. Each atom has to have a p orbital, and notice they're parallel to each other. Okay. Now, when these actually start overlapping, the overlap looks like this. Okay. So this overlap right here is basically this one right here. This overlap is this one right here. Okay. Now, these two things together, these two overlaps, this is only one bond. One pi bond. Okay, this is a sigma bond right here. This is a sigma bond, the S overlapping with the hybrid, another sigma bond. Another sigma bond, another sigma bond right there. Okay, pi bonds will not form until you have a sigma bond existing. In other words, you can only get pi bonds when you have double bonds and triple bonds. Okay. You can, if it's a single bond, it must be a sigma bond. If you have a double bond, one is a sigma, the other one is a pi. You can only have one sigma bond between the same two atoms. So if you end up with a triple bond, okay, one of them is a sigma, the other two must be pi bonds. Okay. Now, if this bonds to other things, this has to be a sigma bond. If this bonds to other things, that also has to be a sigma bond. Okay, if you have something bonded like that with another double bond like that, okay, that's a sigma, that's a pi. That's a pi, that's a sigma. Okay, top one doesn't have to be a pi, but one of them has to be a pi, one of them has to be a sigma. Sigma bonds will always be single bonds. You cannot have more than one sigma bond between the same two atoms. Okay, now, the hybrid orbitals can only be used to create a sigma bond or hold non-bonding electron pairs. That's why when you're trying to figure out the hybridization, you count the single bonds, which are sigma bonds, and you count the non-bonding electron pairs. Okay. Pi bonds have to be formed by an overlap of p orbitals. So each atom that is bonding, if you have one atom here, it has to have at least one p orbital that did not hybridize. So here's the review question. First, draw the Lewis structure for C2H2. Okay, and we've already done this. You can go look in your notes also. And from that, determine how many sigma and how many pi bonds exist between the two carbon atoms.